A2 Further Maths, Isometric Graphs. Okay, so what I'd like you to do is just see if you can move any of the vertices on any of these four graphs to show which ones are exactly the same. And once you've spotted which vertices you'd swap to where, just try to pair up which vertices go with the letters of the other graphs. Okay, so just pause there, have a go, see if you can find out which ones are the same. Okay then, let's have a look at this first one then. So what I'm trying to do is I'm trying to move the vertices anywhere I like so they look the same as one of the other three. Alright, doesn't matter which one you pick. So what I'm going to do is I'm just going to move some of these about. So I'm going to pull that E value just over here, that E vertex. Alright, keeping those same edges. Not made any difference there. Let's just flick the A down here. Alright, again, it's only connected to D, that's fine, I haven't changed it at all. And just to drop D down, just to really emphasize that, oh look, this graph here and this graph here were exactly the same graphs. A is the same as J, D was the same as I, B was the same as G, C was the same as vertex H, and E was the same as vertex F. Those two graphs are the same. I could try that same idea with this, couldn't I? Alright, do a bit of moving about. Oh look, O can move to there, still connected to L and K. And it doesn't matter what else I do then, there is no way I could get that graph to look like any of the top two. Right? It doesn't matter what I try to do, because of the way it's connected up. Alright, so those two graphs are not the same. That one's definitely different. What about this one? Can we get it to be the same as that, or maybe one of these? I could, couldn't I? I could move R across, still connected to P and T. I could move maybe S up, still connected to P, T and Q. And then just to make it definitely the same, I can see that Q can come down there. And oh look, that graph there was exactly the same as those two graphs. So those three, well, I don't know if you spotted it, were identical. They're called isomorphic graphs. You can certainly compare the vertices. We can see that F and R is equivalent, R and P, G and P, and so on. So if two graphs have exactly the same, right, there's a couple of rules, exactly the same amount of vertices and edges, and are connected in exactly the same way, they're called isomorphic graphs. So on those previous ones, even though one had the same amount of vertices and edges, it couldn't be connected in the same way, so it wasn't isomorphic. Whereas the other three could be, by moving about the vertices, be shown that they were exactly the same, therefore they were isomorphic. Alright, so just pause there, just get your last little bits of notes down. Right, now of course it's not always easy just to spot how you could actually move it. So there's got to be a better option than just trying to redraw the graphs and shuffle the vertices about. Now you can do it by checking the number of vertices first of all. Alright, so if these two graphs are going to be the same, they must have the same amount of vertices. Now we can see on this one it's got 4 vertices, this one here has got 4 vertices, so if it passes the first check, definitely got the same amount of vertices. 4 vertices on both, therefore that's fine. The second thing must have the same amount of edges. Right? They're not going to be isomorphic, they're going to be exactly the same if they don't have the same amount of edges. So this has got 1, 2, 3, 4, 5, we can see that. This one's got 1, 2, 3, 4, 5, excellent, both got the same amount of edges. Now that's not enough to make them isomorphic, you need to be careful, there's got to be another rule as well. The other thing you need to check, this one's slightly tougher, is the order of the vertices and the way they're connected the same. Okay, so if I look at the order of these vertices, I can see it's 3, 2, 3, 2. This one here is connected in that sort of pattern, 3, 2, 3, 2. If this one can be drawn with the order and create that same pattern, 3, 2, 3, 2, they will be isomorphic. So 3, 2, 3, 2. And I can see that if I do it that way round, I can get this same cyclic pattern. So therefore, these two graphs will be identical. They will be isomorphic. All right, so the number and the size of the cycles must be the same. So therefore, it's ticked off all of those two, but there is a slight problem. That graph there has a cycle order 3. Okay, so that one there is a cycle order 3. This one here is a cyclic order 3, so that's fine. We've got 2 cycles, order 3. And it's got a main one around the outside, cycles order 4. This one, cycle order 3, cycle order 3, and a cycle order 4. They are definitely isomorphic because they pass those 4 checks. Are they? Do they have the same amount of vertices? Do they have the same amount of edges? Do you get the cyclic order the same? And do you have the same number of cycles in each? As long as it passes those 4 checks, the graphs can be said to be isomorphic. Okay, just pause there, take down what you need. Right, so what I'd like you to do, sticking with your notebooks, copy down this question. They look the same, don't they? So determine whether these 2 graphs are isomorphic or not. So I'll let you have a play on your own. Try following the 4 rules. See what you find. Okay, so let's just go through the different rules then. So the first thing you should have checked is the number of vertices, and you can clearly see they both have the same amount of vertices. They've both got 6 vertices. Okay, so that's a definite tick off for the first one. Do they have the same amount of edges? Because that could be the one reason. Yes, they both got exact same amount of edges. These 2 might be connected in a slightly different way, but they definitely got the same amount of edges. Do the order of each of the vertices, or the order of each of the vertices, is it the same and connected in the same way? So for example, if I looked at going round, I would be going 2, 3, 3, 2, 3, 3, back again. Perfect. What about this one? 2, 3, 3, 2, 3, 3. Absolutely spot on. So I'll clearly say that those 2 are definitely going to be isomorphic so far with the first 3 checks. But then you get to the last one. Graph 1 has a cycle of 3 edges. Okay, a cycle of 3 edges. But there is no cycle of 3 edges in graph 2. It doesn't matter how hard you try, you're not going to get an equivalent cycle to that. Okay, doesn't matter how hard you try, there is no cycle with 3 edges. So therefore, although everything was looking hunky-dory to start with, everything looked like it passed, and it did. Once you got down to the cycle test at the end, we've got a cycle of order 3, but there is no cycle of order 2 in that graph, so therefore those 2 graphs are not isomorphic. It doesn't matter how hard you try to rearrange this graph, you are never going to be able to duplicate that graph. All right, so you need to be very careful. Graphs that look very similar aren't always isomorphic. Okay, so what I'd like you to do, see if you remember how to fill in adjacency matrices. So have a go at completing the adjacency matrices for each of those original 4 graphs. If you remember, they're the ones you started the lesson with. Okay, so let's see how you did. So what you're looking for is putting in a number if they're connected. There's a 1 and a 0 if they're not. So are A and A connected? No. So it's a 0. B and A? No. C and A, but D and A are connected with a 1. All right. Whereas B is connected to D and E, so the one's in there. C is connected to E and D, so those 2 are connected. D is connected to 3 of them, A, B and C. And then finally, E is connected to B and C. So I end up with this adjacency matrix. What if you've forgotten how to do it? Have a go at the other ones yourself. Make sure you know how to do it. Okay, so just quickly going through it then. Yes, F is connected to G and H, G is connected to F and I. We can see that I is connected to G, H and J. So we've got that. G, H and not J, sorry. And J is connected to just I. All right. This graph, we can see what K is connected to. We can see what L is connected to, and so on. All right, so just confirm we've got the same answer. And then finally, this one, P is connected to R and S. Q is connected to just S, R is connected to P and T, and S is connected to T, P and Q. And then finally, T is connected to R and S. So you should have just gone through and worked out each of those adjacency matrices. Now we know those 2 were isomorphic, but without doing any sort of manipulation on the graphs, without doing all the graph checks, show the adjacency matrices are equivalent. How could you show that these adjacency matrices are equivalent without rearranging the original graphs themselves? So say you just had these two. All right, so have a think about it. How could you do that? Okay, so what you're trying to do is maybe just swapping the rows and the columns about. Instead of having A, B, C, D, E, I could have had A, B, E, D, A, B, C, E, D. These two could be swapped around. Now, can you actually see any columns that you could potentially swap around so that it looks exactly the same as this? Okay. And if you think, actually, look at the top line here. Right, the top line is 0, 1, 1, 0, 0, and that's the same as the E, and it's 0, 1, 1, 0, 0. If I could swap the A and the E over, if I just swap the A and the E over, will I not just end up with exactly the same? All right, if I swap the A and the E, or the F and the J, if I did it on this one, it doesn't matter which way you do it, A and E, F and J, then look what happens. So the F and the J are swapping places, so the J can be written at the top, all right, and J can be written down. F can be written across there, put J down, put the F down, and oh look, lo and behold, this graph here, this adjacency matrix here, is absolutely identical to that adjacency matrix there. And also what's nice about the adjacency matrices, you can see exactly which vertices are equivalent. A to J, B to G, and so on. Alright, so you've got exactly the same matrices there. Notice it doesn't make any difference which round you've got the G to H as well. So B could go to G or B could go to H. Alright, those would be fine. So those two could swap places and it's still correct. Right, if you get two identical matrices, then the two graphs, of course, are isomorphic. So you can actually show it using the four rules, the vertices, the edges, the cycles, and the order cycle check. Or you can show it by comparing adjacency matrices. Okay, so just in your notebooks, just get that question down. See if you can write down those two matrices. And you're just trying to show that those two are isomorphic. So what I'd like to do is just have a play with it yourself first. See if you can work it out yourself. Okay then, let's see what we can do. So I'm going to swap P and Q over. It's not as straightforward as last time because it didn't actually work out straight away. But I'm thinking if I just swap P and Q over, then at least I can get that 1 in the position of that Q because they look the same, don't they? 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. These two aren't the same, but let's just try that first. So I'll swap my P and Q over and I've ended up with this graph. Now, if they're isomorphic, right, my goal is to try getting this to look the same as graph 1 or vice versa. Is it almost there? Maybe. Maybe if I can do one more swap, I'm going to swap T and R over. Now, if I swap T and R over, that's going to get me in this position where T and R can be swapped places. So I can put T straight down. So T goes down to here, right? 0, 0, 0, 1, 0, because don't forget the R swap places as well. So that's gone down to there. And the R swap places with that one. So therefore you end up with that. Those two graphs are exactly the same. They are equivalent to each other. And so because those two are equivalent to each other, what I can do now is I can say that graph 1 and graph 2 are definitely isomorphic because the two adjacency matrices are the same. And I need to do the equivalent vertex labels, right, by saying which vertices were equivalent to which. So in this case, we've got the vertices that are equivalent are going to be A to Q, B to P, C to T, D to S, and E to R. They might also ask for a sketch, and you can do that yourself relatively easily by just putting down the 5 vertices and just joining them up. Same with this one, to show they get exactly the same answer. Okay, so what I'd like to do is just have a go at completing the exercise on 1.4, or exercise 1.4 on page 14.